Hi students, hope everyone is fine and safe. It gives me immense pleasure to welcome you all to my new video, and today's video is about another interesting concept in the subject electrical and electronics engineering. We're going to see the construction and working principle of PN junction diode. This video is very important video. This is very basic video for any electronics and communication engineering student, right? So in previous video, we have just given the overview of semiconductors. What is N-type material? What is P-type material? I would recommend you people to go through that video first so that you can easily understand the working of PN junction diode, right? So with this, we will start the theory of PN junction diode. So what is a PN junction, right? If you take a diode, right? Diode is a component which allows electricity in one direction and blocks electricity at the reverse direction, right? And we're going to say this as a PN junction diode because it is constructed using a P-type material and N-type semiconductor material, right? If you're going to join an P-type material and an N-type semiconductor material, then that forms a PN junction. You can see this is called as PN junction, right? And the diode right now which we are seeing is called as PN junction diode. That's because we're going to combine the P-type material and the N-type material, and the junction formed is a PN junction, right? And already we know that in N-type, majority carriers are electrons and minority carriers are holes. Whereas in P side, in P-type material, holes are majority carriers and electrons are minority carriers, right? And we will see the working. Before that, you have to understand the symbol of PN junction diode. This is the symbol of PN junction diode, where this line indicates that this is a cathode, which is negative terminal, and this is positive terminal, right? And practically the diode will be like this. Using this ring, the silver ring, we can able to identify which is cathode and which is anode, right? And to start with the working of PN junction diode, first you have to understand how a depletion layer is created, right? So what is in the depletion layer, right? If you're going to combine this P and N type material, that is, we call it as PN junction, without any biasing, without any electricity, without any supply, right? Normally what will happen, we know that in N type, electrons are majority carriers, and in P type, holes are the majority carriers, right? And there is a process which is called as diffusion. Diffusion. What is diffusion? The movement of charge carriers from higher concentration to lower concentration, right? That is called as diffusion. The process of movement of charge carriers from higher concentration to lower concentration. So now here electrons are at higher concentration, whereas electrons here is lower concentration. So electrons will flow from N side to P side. Similarly, holes here are higher concentration, whereas here holes are lower concentration. So the holes will move from P type to N type due to diffusion, right? And during this diffusion process, that is electrons crossing from N type to P type and holes crossing from P type to N type, right? It crosses this junction. During this process, what will happen? Recombination will take place. What is recombination? That is, we know that hole is nothing but a blank space, that is hole, and you have an electron here, and when this electron and hole meets, it will recombine and form an electron hole pair. It creates electron hole pair, right? So whenever the electrons and holes meet each other, they form electron hole pair. Recombination will take place around this junction of PN junction, right? And during this recombination of process, right, a positive ion will get settled at the boundary of N-type material, and similarly a negative ion will be settled at the boundary of P-type material. And these ions are immovable ions. These ions are immovable ions. Immovable ions. Right? And these immovable ions, as it increases, it will stop the diffusion process. It will stop the movement of charge carriers from n type to p type and p type to n type, right? That is, this region will be depleted of charge carriers. There will not be any charge carriers. There will be only immovable ions, right? This region will be depleted from charge carriers, free moving charge carriers, and that is why it is called as depletion region, right? And because of this depletion region, no charge carriers, no majority charge carriers can flow from n type to p type or p type to n type, right? And this depletion region, right, you'll have positive ions and negative ions, and there will be an electric field that will be set by this ions. That is, it will flow from positive to negative, from positive ion to negative ion. There will be an inbuilt electric field will be set because of this ion, right? And there will be an electric field in this depletion region because of this this immovable ions, right? And this electric field will be a barrier for movement of charge carriers, right? And it is called as potential barrier. It is called as potential barrier. So if any majority carriers want to move from n type to p type or p type to n type, then it has to overcome this potential barrier to have current conduction. This is the formation of depletion layer, right? So you have to understand how the unbiased p-n junction diode works, right? So because of diffusion process, the majority carriers will move, and because of this movement, recombination will take place, and because of recombination, positive ions will be settled at the boundary of n-type material, and negative ions will be settled at the p-type material, boundary of p-type material, which is immovable ions. And this immovable ions, as increases, it stops the movement of majority carriers. And there will be an electric field set between this movable ions. That electric field creates a potential barrier for this majority carriers, right? And now, for any conduction to take place, then this potential barrier has to overcome, right? And depending upon the material, the potential barrier, the value of potential barrier varies. Say for example, if you take silicon, the potential barrier will be 0.72, whereas for germanium it will be 0.3 volt, right? So whatever I said, it is explained in this slide, and now you understand how a depletion layer is created, right? And now we'll see the working of p-n junction diode based upon the biased condition. So far we have seen unbiased condition without providing any supply, and now we're going to see what happens during forward biased condition. During forward biased condition, if you say forward biased condition, we have to give positive to the positive terminal and negative to the negative terminal. That is, positive to the positive terminal to the positive side and negative terminal to the negative side. Negative side in the sense, we have majority here electrons which are negative side, which are negative, and these are positive ions, positive holes, right? And when you're going to forward biased, the electrons are negatively charged, and if you're going to give negative charge here, what will happen? It will cause repulsion, right? It will cause repulsion. So obviously the electrons will start moving towards p side, right? And similarly, the holes here is positively charged, and if a positive terminal is given here, right, it will cause repulsion, and electron and holes will start moving towards n side. It will repel towards n side, and the electrons will move towards p side, right? And if you're going to increase this forward bias condition, initially there will be a small movement of majority carriers here and there, and as you increase this particular voltage, the forward biased voltage, I have already said there will be a potential barrier for any semiconductor material, right? It is 0.72 for silicon and 0.3 for germanium, right? And if you're going to increase this voltage beyond this barrier potential, right, or else we can also say that the moment of majority carriers will gain sufficient energy to overcome this barrier potential, right? So once it overcomes, it breaks this barrier potential, then current conduction will take place, right? So if you're going to keep on increasing the voltage beyond this barrier potential of the semiconductor material, then obviously the flow of electrons will increase from N to P, and flow of holes from P to N will also increase, right? And this moment of charge carriers results in conduction of electricity. This is what happens in forward bias condition, right? And you can see, as I said, a positive terminal is connected to a P type and negative terminal is connected to N type, that is forward bias condition, which eventually result in movement of charge carriers towards the other end, right? And if you're going to constantly increase the temperature, it will overcome the potential barrier and current conduction will take place. And you can see in forward bias, this is the forward biased voltage. If you're going to start increasing forward biased voltage from 0, right, and slowly the conduction will start, and as soon as it reaches, for example, if it is germanium, if it is more than 0.3, then obviously current conduction will increase after 0.3, right? And if it is silicon, right, and if you're going to increase the forward biased voltage more than 0.72, the current conduction will increase after 0.2 because it breaks the potential barrier, right? So whenever the forward voltage is greater than the barrier potential, then current conduction will take place. And what happens in reverse bias condition? Normally in reverse bias condition, there will not be any flow of electrons. That's because here we already know about potential barrier. If it is reverse bias junction, reverse bias condition, we will give positive terminal of the battery to the N side and negative terminal to the P side. So what happens here? We know that here holes are majority carriers and here electrons are majority carriers. And because of opposite charges, the electrons will get attracted here towards this terminal and holes will get attracted towards this terminal, right? And this attraction causes the depletion layer to increase. And because of that, right, the depletion layer will increase, the barrier potential will be very strong here. So obviously there will not be any conduction takes place because there will not be any movement of majority carriers, because all the majority carriers are attracted towards the other end, which causes the depletion region to increase, right? And definitely there will be small leakage current or small reverse saturation current. That's because of the minority carriers. We know that the minority carriers here are holes, where the minority carriers can slowly sneak through and reach here, and similarly the electrons here, the minority carriers can slowly sneak through here in this reverse bias condition. And because of that, there will be only minimum current, that is microamp current will flow in reverse bias condition, because the depletion layer is it's widened and it is very, very strong here, right? And that is what happens in reverse bias condition, right? As I said, there will be only few microamps of current which flows because of minority carriers, right? And you can see this is the characteristics of PN junction diode at reverse bias condition, where at the reverse bias condition only microamps of current will reach, and there will be a certain condition where definitely there will not be any current flow. There will be a very minimum of current flow due to minimum minority carriers. But if you're going to keep on increasing the reverse biased voltage, there will be a breakdown which happens at one particular terminal, at one particular point, right? And at that point, the breakdown will happen and the conduction will take place at the reverse direction, right? So that voltage where breakdown happens, that is called as breakdown voltage, right? And whereas this happens after certain limits, that more large number of free electrons are formed, that then results in avalanche breakdown, which causes a very high large reverse current to flow through, right? And to combine this forward biased and reverse biased, you have to understand the VI characteristics of PN junction diode. As I said, in forward biased condition, the current conduction will take place slowly initially, and once the applied voltage exceeds the barrier potential, current conduction increases. Similarly, at the reverse direction, there will be a minimum current due to minority charge carriers, and if there is a breakdown happens because of very high reverse voltage, then there will be a sudden increase in reverse current, right? So this is the VI characteristics of PN junction diode, right? We will see the application of PN junction diode because of this characteristic, that is it can able to transmit current in one direction and arrest the current at the reverse direction. It can be used in rectifiers, it can be used in digital logic circuits, it can be used in clamping networks in TV receivers, voltage multipliers. It can be used in clipping circuits as well in radio and TV receivers, computers, and it can be used in demodulation circuits as well. And this PN junction diode is very basic diode, whereas we can have different varieties of these diodes depending upon the doping concentration and the materials which we use. Like for example, it can be used as detectors in optical communication circuits. There will be Zener diodes in voltage regulators, varactor diodes in tuning radio and TV receivers, light emitting diode in displays, laser diodes in optical communication, and tunnel diodes in relaxation oscillators, right? These are some special applications where depending upon different concentration of PN junction diode, right? So today what we have seen is, we have seen the construction, working principle, and VI characteristics of PN junction diode. I believe this video will be very useful for you. Thank you, my dear students.